Today I'm going to talk about clouds, which you've already heard about. I'll talk about methane, which you've already heard about. I'll talk about biosignatures, which you've already heard about. But I'll talk about them in the context of another planet. So I've chatted with some of you last night at the happy hour and then also throughout the day today. And so instead of starting the talk with the 7 minutes of terror or the sky crane landing event that we had about a year ago, I figured I'd start, since you're a tech crowd, I'll start with a test. Can anybody tell me what this is? Besides, it's an equation. It's the rocket equation. It's sometimes called the ideal rocket equation. And it's what relates change in velocity of a rocket to the exhaust speed coming out of the rocket and the initial and final masses. And I can tell you that this is not what inspired me to become an aerospace engineer. Although I did have to learn this. Anybody know what this is? I don't know how easy it is to see for the folks up front. So, yes, so nobody said South Utah, which means there's probably no conspiracy theorists in the room who are thinking that we're staging this whole thing. That's exactly right. This is the surface of Mars from Viking 2 in 1979. And again, it's probably tough to see with the lighting, but for those in the back, that's snow on the ground. That is water ice that precipitated out. These water molecules bonded to dust particles in the atmosphere and precipitated out to the ground. And we're left there for about 100 sols, 100 Martian days on the surface. Now, when I was a kid and these pictures were coming down, this is the kind of thing that inspired me. We didn't have the internet, we didn't have the ability to get these, and so you'd wait for the next round of encyclopedias to come out and go to the library, right? Some folks remember that. And it was pouring through pictures like this of being on another planet, pictures from another planet, a second data point from where we are here on Earth that inspired me. So we've been exploring Mars for quite a while now. Why are we going there? So I want to start with this trailer from a JPL documentary that was put together recently called The Changing Face of Mars.
Hello, I'm John Fitch. Man, since the beginning of time, has wondered about the stars and planets. Our neighbor planet Mars has intrigued the imagination of artists and writers. Some people think there is life on Mars.
I see a vast network of channels crisscrossing the planet. Obviously the work of intelligent Martians. The simplicity and symmetry cannot...
It will be possible with larger telescopes to see cities on Mars, to detect navies in the carbon.
The inhabitants of Mars are vast, cool, and unsympathetic intellects, looking across space at the planet Earth with envious eyes. Are they planning an invasion?
We've been looking at Mars the way artists and writers imagine it. A planet of jungles and deserts, inhabited by monsters, of course, beautiful women. Well, I'm happy to say that they are wrong. Mars is far more mysterious than that, and far more surprising.
Of all the planets in our solar system, Mars has always held the most fascination. There is no longer hope of little green men. But the question of whether microbial Martian life might have once, or still might exist, remains.
So it was really only the 1960s before we were able to dispel it. There were credible astronomers, Percival Lowell for one, that were looking at Mars through telescopes here on Earth and seeing these things that looked like canals that could only have been made by an intelligent group of people, or group of Martians in this case. And it really wasn't until we started doing flybys and sent spacecraft in orbit around Mars in the 1960s that we were able to dispel those myths. And so things like War of the Worlds and all that persist in the American imagination. The first credible attempt to envision what it would be like to land on Mars came about by the great aerospace engineer Wernher von Braun and his team in 1956. And what he envisioned is a hypersonic spacecraft 120 meters in diameter, that by the 1980s we would be able to assemble in orbit and then with 17 astronauts aboard fly to Mars and land on skids at about 100 miles an hour. What Wernher von Braun didn't know is that his assumption that the atmosphere on Mars was about 1/10 of the Earth's atmosphere was incorrect. And with what we know now and what we've learned since through the orbiters and certainly through the landings that have been attempted by humanity, that the atmosphere is actually only about 1/100th of what it is here on Earth. And those 17 astronauts, had they embarked on this mission, would have attempted to land at 1,000 miles an hour on skids. That would not have gone so well. So landing in the trying to get to the surface of Mars started in the early 1970s by the Russians. And as you can see here, very much like even when you look at all missions that try to go into orbit, but certainly missions that try to land, humanity's only batting about 40% in terms of landing. And you'll see in this case, when it comes to Mars, the US seems to be the country most successful with Mars. For the Soviet Union and now Russia, Venus tends to be their planet. We don't do so well going to Venus, and I'm not sure why that is, and don't read anything into that. But I want to talk to you. Women, never mind. So what I'd like to do is take you a little bit through the evolution of Mars landing, Mars past, where we are today, and certainly the future of Mars exploration. And for the United States, that all started in the mid-1970s with the 2 spacecraft that we sent in the mid-1970s that took that picture of the snow out there on the surface of Mars with Viking. And what we proved with Viking is that we could land through the use of a supersonic parachute, a heat shield that would take the aerodynamic heating from coming into the atmosphere at a very high velocity, on the order of 5 or 6 kilometers per second. And then fire liquid-fueled throttleable engines to slow it down, and then land on legs. These were fixed vehicles, so they're landers, not rovers. That's the distinction that we like to make. And they were nuclear-powered and persisted on the surface for several years, giving us a tremendous amount of good science and really giving us ground truth that Mars is a cold, dry desert of a planet. It would be 20 years before we would go back to Mars. And on morning of July 4th, 1997, we landed the Mars Pathfinder mission with the Sojourner Rover on board. And there we took the same heat shield concept and supersonic parachute, but this was the first Mars mission in the faster, better, cheaper era of NASA. And so instead of using expensive liquid throttleable engines, we went with solid rockets that were mounted on the back of the back shell there, which is part of the entry capsule. Those would slow it down, and then we figured instead of trying to slow it down gently and have it land, let's just inflate airbags around it like a soccer ball, cut the tether, and bounce it to the surface. Then deflate the airbags and land. And for faster, better, cheaper, that proved to work quite well. We were able to demonstrate and learn what it means to operate a vehicle on another planet where the one-way light time, so the time it takes the radio waves, the time it takes our commands to get there, varies from about 4 minutes when Earth and Mars are closest to about 22 minutes when they're on opposite sides of the sun. So we can't sit there and joystick. And so we learned the very basics of what it means to autonomously rove on another planet. That was followed up in 1999 with Mars Polar Lander. And in this, we went back to the legged lander concept that we had with Viking. We didn't want to go all the way to throttleable engines. And so what we did was we used pulsing of liquid fuel engines. Again, very similar technologies. This was faster, better, cheaper. So there was no requirement on us to have telecommunications and radio all the way through entry, descent, and landing. And so from the time that we ceased communications with the vehicle as it performed entry, descent, and landing, we never heard from it again. We've tried over the years to photograph the area where the Polar Lander should have landed and have been unable to identify anything. There are multiple credible failure modes that could have happened that day. The most likely one is that when the legs deployed, that bounce was sensed by the accelerometers on board, which said, touchdown, cut the engines, about 40 feet above the Martian surface. And that would have been enough with Mars gravity, which is about 3/8 Earth gravity, to smash the Polar Lander all the way to the ground. So we tried to recover from that, and we recovered from that in the year 2000 by looking back to Pathfinder, to our most recent success. We were still coming out of the faster, better, cheaper, but we went with a concept that used the same airbag type of landing approach. And that's what led to the Mars exploration rovers, Spirit and Opportunity, which, as you both know, or you all know, nearly 10 years ago, we bounced the 2 of them onto the surface of Mars using the same solid rockets, the same airbag concept. And they were both solar powered, so they were only expected to last about 90 days because we figured the solar panels would get covered in dust, unable to generate electricity, end of mission, unable to keep itself warm. What we found is, as a cold, dry desert, the dust devils come around on pretty much 30 to 45 Martian day centers, clean off the solar panels, bring our power right back up again. Spirit lasted 7.5 years into its 90-day mission, and it ended up getting stuck in sand at an altitude that didn't give it sun in the winter. And Opportunity is coming up on its 10 years on the surface. So as a humanity, we've had a continuous presence on the surface of Mars for almost 10 years as of the beginning of next year, which is pretty significant. We followed that up by trying to use spare hardware from the Mars Polar Lander, which was a pretty scary proposition. We named the project Phoenix because we were rising that hardware from the ashes, and this time we were going to make it work. So we had to figure out what went wrong to the best of our ability without having any telemetry to tell us, and then ensure ourselves that the risk was appreciably low that we would fail this mission. And we sent Phoenix to the north polar region of Mars in 2007 to an area where from orbit we could see vast amounts of hydrogen. And what we found is just below the surface, as you can see in the scratch marks there, there's water ice, significant water ice, just below the surface of Mars. So we've been kind of following the water with the last few missions. Around the same time that we started developing the Mars exploration rovers, we started envisioning a mega rover. A rover that was doing more than just proving we could drive around on another planet, doing more than just trying to understand if that one thing we were seeing from orbit is water or not. And to actually create a robotic geologist, a scientist with full lab equipment that can go around and do science on our behalf on the surface of Mars. So we envisioned this large rover that could even carry potentially in situ resource utilization capabilities, the ability to take the atmosphere and turn it into water, things like that. So we had to figure out how to get it there. And obviously, the initial concepts were about as blue sky as you can get, but this one wasn't one of them. So we developed a taxonomy of the various landing techniques that we've created. And if you think back to that chart that I had of all of the different failures and successes that we've had in trying to land, the designs were all vastly different. We don't yet have a perfect way to land on Mars. And I can tell you the sky crane method for Curiosity is not the perfect way. It's a very good way for this vehicle, but to go larger, it would not work. So we had to develop a way to communicate with each other about the various options that were at our disposal. So we looked at legged landers. We looked at taking this mega rover, this thing that we envisioned was probably going to weigh about 2,000 pounds, and started looking at a legged lander. Well, on slopes, legged landers don't do well, especially if you put a lot of mass way up high. They're not very stable. So legged landers with outriggers. Okay, if you've got now a 2,000-pound vehicle on top of a lander, you're going to need very heavy ramps to get it off. You have to fly those and land those all the way to Mars. Try mounting it underneath, as the picture over there on the right shows. Also, very challenging. What happens if you're on a rock? You may never get out from underneath the lander, and you may have created a lander unto itself. Huge airbags. It's a concept we know and love from Pathfinder and Mars Exploration Rover. The size of the airbags for this led to concerns over whether we would even be able to drive out of the airbags. Would we need cutters? Would we end up with so much airbag material and debris that they would clog all of the mechanisms? So it was one possibility. A lander pallet, a descent stage that essentially throttles all the way down to the surface, serves as egress ramps. There are a lot of stability issues there as well, particularly on any kind of slope or with any kind of rock obstacle. And so we started thinking about Pathfinder. We said, what if we replaced those solid rockets that were there on the back shell with liquid rockets that were throttleable so that we could slow the descent and slow it enough that we didn't need the airbags because those were problematic? What if we had it land on its wheels using this throttled descent and then cut the rope and had the descent stage or the back shell fly away? And we decided that was absolutely too crazy. It was never going to work, and so we shelved that idea. And as we worked through each of the different concepts, went back and forth, someone would keep bringing this up. Hey, what about that Pathfinder-based concept? That does pretty well when it comes to slopes. That does pretty well when it comes to large rocks that are in our landing area. That does pretty well in the wind. And so kept coming back, and it took about 3 years. And after about 3 years, consulting with helicopter pilots, entry, descent, and landing experts from all over our agency, former astronauts, we decided this was just crazy enough to work. So, we stopped to think about how we go about challenging each other and allowing a concept like this to take hold. And we refer to that at JPL as a culture of criticism, which can be pretty negative, or a culture of critical thinking, certainly. But the criticism is about the design, and it's not personal. We're not criticizing each other. But it's something that's not, many of you work for tech companies where you'll have a design, you'll hold a design review, and we're critical of each other in design reviews, and that's a venue where everybody expects to have your design critiqued, maybe your requirement set critiqued. What I'm talking about here is a persistent culture. Hallway conversations get critiqued, and people are constantly pushing. Nobody takes a fact for granted. Well, until it becomes a proven fact. But nobody takes a statement for granted. Nobody takes a design concept for granted that this is going to work. And so we're constantly challenging each other so that somebody may throw off a design and say, yeah, but that's going to tip over 50% of the time when we do Monte Carlo simulations. Well, this design actually could get us even more mass to the surface, so we can do even more science. Certainly the designs have to be testable and or analyzable. Otherwise, we'll never have confidence because we're never going to be able to do entry, descent, and landing before we do it for real at Mars. And so ultimately, this type of culture of construct is what gets us to the right design in a way, again, that is just intuitively focused on the design and not the people, and happens constantly. So what you end up with is a concept like this, the sky crane maneuver. And these pictures here show where we hit the top of the atmosphere at about 13,200 miles an hour, and 7 minutes later, we've hopefully come to rest at about 1.5 miles per hour as the instantaneous speed right before. Anything more, it gets to be a little too much. We used a supersonic parachute, and I've got some parachute material outside if you guys want to feel. This is a 100-pound parachute that inflates with like 70,000 pounds of force. And then we drop out of the back shell in powered flight. The rover lowers itself. The CPU for all of these operations are inside the rover. So the rover is controlling everything. There's an electrical umbilical that runs between the rover and the descent stage for throttling the engines, getting the gyro information out of the descent stage for lowering for the descent. So you ask yourself, is NASA risk averse? From you look at this, you say, no, NASA, look, we take all kinds of risks. And I can tell you, and I heard some yeses in the audience, NASA is very risk averse. But there's probably two edges to the sword. One is, we are willing to embark on missions that have inherent risk, trying to push the boundaries, knowing that we might fail. But the path that we take to get to trying to accomplish that mission, we try to beat down the risk as much as we can. Right? We try to take the lowest risk approach to tackling that risky endeavor. And that's, I think, where as an agency, we are very risk averse. And it's that path of getting there that ends up getting paved with the new ideas, pushing the limits of different subsystems and different technologies, so that ultimately on landing night, even if we cratered in, which I had hoped we didn't because we found out about 2 hours before landing night it was being broadcast live in Times Square, which was hard enough for us to take. Even if we cratered in, we knew that we had made significant advancements, that we could push into the next exploration activities that we do on Mars, Europa, Titan, various places that may have been habitable, may currently be habitable as well. So what we end up with from 1956, from Wernher von Braun's first concept, is we end up with the Curiosity rover, 2,000-pound laser-wielding robotic scientist and explorer. So I'd like to talk for a moment about the name. 3 years before landing and about 2 years before launch, NASA held a naming contest. We teamed with Disney, Wally, and put together this naming contest. And several names were chosen as the finalists. Ultimately, there was a 6th grader from actually Lenexa, Kansas, which I understand is not very far from here. Got some shout outs for Lenexa. So Clara Ma came up with the word curiosity. And that was chosen. I think 65,000 or so people voted, and that was what was chosen. And I can tell you, no offense to Lenexa or to Clara, she's now a summer student coming out to JPL every summer working with us. But the team hated the name. We hated the name because we had designed the biggest, baddest, beefiest vehicle that we were going to attempt to land using a sky crane maneuver on the surface of another planet after flying 350 million miles in like 250 days, right? So you can do the math, a little more than 1 million a day. And we were calling it Curiosity. It wasn't science fiction enough. It wasn't strong enough to us. We wanted to paint flames on the side of this rover just to show everybody how big and bad it was. But as the systems came together, and as we started testing this vehicle, and as we would put the spare vehicle in the Mars yard, which we have at JPL, and the team in the control room, and try to do exploration of local Pasadena through this rover, we really began to appreciate the name and appreciate that it's that curiosity that drove us to be willing to do the sky crane maneuver. It's the curiosity that drove us to embark on this mission in the first place, right? Just to give you a little quote from that mission, from Clara's essay, where she describes, and I'll do it as other speakers have done so I can read it a little better, where curiosity is the passion that drives us to become explorers and scientists with our need to ask questions and wonder, even in the face of risks and dangers, continuing to wonder, dream, create, and hope. And that's what we all did as we were building and designing this. That's what we all did, certainly on landing night. That's what we're doing now. And as I describe some of the discoveries that we've made and where we're going with Curiosity in the future, you'll see that the name continues to be as appropriate as any I could think of. So what's the impact been since landing? So I've worked space telescopes, I worked Hubble, I've worked UV, gamma ray, all kinds of things. I've never participated in a project with the kind of public interest and public impact, and I attribute that to Curiosity as well. Not the rover, but the trait that's inherent in all of us. Just quickly to share some of the events, the weeks leading up to landing night, for me, we had more media than we had seen on JPL in a long time, constantly doing television interviews and TV spots for news or documentaries that were coming out. Shortly before landing, we were identified by GQ magazine as, GQ every year names a Man of the Year. And for the first time, they named a Team of the Year. And they called us the Space Men and Women of the Year. And as you can see in that red picture, red circle, as I remind my wife, she's now married to a GQ model. And I have proof right there. Yeah. So we all get a little something out of the projects we work on. So landing night. So I'm no longer a console jockey. I'm not the ones that sit in mission control. That was my team that did that. And so I spent the hours leading up to landing every 15 minutes doing a different interview. We had 1,000 media folks on lab that evening, as well as political dignitaries, folks from the entertainment industry that have helped us with voiceovers or public service announcements and things in the past. So some of the highlights for me, I got to meet June Lockhart from Lost in Space, she's very cool. Abraham Ben-Ruby and Seth Green. And I have to say, I was so busy working on this project, I didn't really know who Seth Green was. I only knew the name. And so when this picture was taken, he actually had volunteered to take the picture, and everybody started laughing, except me, because I didn't know who he was. And of course, Will Wheaton, because you can't have anything related to space anymore without Will Wheaton. So the public impact of Curiosity and the Mars Science Laboratory mission has recently been captured by our production crew in a quick video about the impact of landing, and I want to share that with you now as well.
This big, huge parachute that we've got, it only slows down to about 200 miles an hour. But we've got to cut it off and then come down in a lot.
Nation, it is a proud day for America. Our flags are flying, and we're singing that verse of the national anthem with all the curse words in it. Because at 1:30 a.m. America Standard Time, NASA's Curiosity rover touched down on the surface of Mars. We Marsed it!
Space nerds and gamers, the space agency has teamed up with Microsoft to create a Mars Rover Landing Connect game for the Xbox 360.
That's a fun one. So I think I'll take this point to apologize that I'm not NASA Mohawk Guy. You didn't get NASA Mohawk Guy to come give the talk tonight. NASA Mohawk Guy, as he became known, is a guy named Bob Ferdosi. He worked on my team, still does, on the mission. And there was an interesting thing that happened. So he worked during entry, descent, and landing. Everybody saw him, and that's what got him very popular. And then he was going to go home and come back in the next day to help out with surface ops. My job, after just participating in mission control, cheering and everything, was to go try to get a couple hours sleep before we got the first data down from initial operations on the surface. And I was responsible for any problems that might come up. I was the anomaly response lead for Sol 0, as we call it, the initial operations. And so Bobak left about midnight, and about 8 a.m. I saw him in the elevator in the ops building. And he said, the funniest thing happened to me. Last night before landing, I had 20 Twitter followers. My girlfriend, some friends from college at MIT and UW, and my mom. I'm at 20,000 Twitter followers in 8 hours. And I think he's up to 60,000 now. So as the team likes to say, we owe all of that to the fact that, so at launch, nobody noticed, but Bobak had an orange mohawk. So he always is doing something with his hair. And so we put together an online poll across the team to pick what color his hair would be for landing night. And of course, we picked red, white, and blue. And then he gave that information to his hairstylist, who did the white stars and everything. But we figure as a team, we were the ones that helped propel him to stardom as an internet meme, I guess. So besides We're NASA and We Know It, which is a great song, in my opinion, what has Curiosity given us so far? So I'd like to briefly talk about the latest from Mars. Certainly we get a lot of pictures. I mentioned the fact that when I was a kid, the pictures showed up in the encyclopedia the next year, or sometimes in brochures that NASA would print and try to get out to the schools. This is one of the earliest pictures that came down from Mars with Curiosity. It's using our hazard avoidance cameras, which are mounted up front, that are really just for driving around. But it shows the science target of Mount Sharp there in the background. It's a 3.5-mile high mountain, which is really where we're headed with the vehicle. Also casts a shadow on another planet, which, having worked on the hardware, and now seeing that hardware cast a shadow on another planet can get you pretty emotional, right? And it does me every time I talk about it. But we make these pictures available. They're essentially bent piped from Mars through JPL out to the internet in raw form so that anyone can take a look at it. We have amateur rock collectors that are poring over these images, looking for something that we scientists and engineers might have missed to try to get us to pay attention or take a look at something. So this person, Righteous5280, sent us this. So I think most of you in the audience would know what this is. So excellent Photoshop skills here. Got the aspect ratio and everything. We didn't follow up on this one. Rover still survived, even with a government shutdown and everything. We were still able to continue. So in terms of real science, one of the first things that we did with the vehicle was we found a sand dune, which we named Rock Nest, and we cozied up to it. And here you can see, this is, again, I don't think we have any conspiracy theorists in the audience. This is not a picture taken by a third person that is on Mars taking a picture. This is a selfie. This is actually a selfie that's composed of 55 separate pictures taken with a hand lens imager out at the end of the robotic arm. And this just proves that 30% of all pictures now are taken are selfies. And so we stitch those together, and so the robotic arm sort of disappears, but it's Curiosity taking a picture of itself. And you can see the bite marks in that sand dune there where we scoop material to analyze. And our big finding, which is just as much a non-finding as anything else, is that Mars dirt is in fact Mars dirt. It's a global phenomenon. It happens everywhere on the planet. We know Mars has dust storms. The dirt that we found on Viking, Spirit, Opportunity, etc., it's very much a consistent, uniform distribution. Okay, well that was important, but not overly stimulating. So then we started drilling. From the time we landed, instead of going towards Mount Sharp, we found an area that from space, about 400 meters away, looked rather compelling. From space, it carried its heat well into the evening. It has high thermal inertia. So we knew there was something different about that area. So we drove over, and we drilled for the first time on another planet. So that top picture you see there is the first hole ever drilled on another planet, which, ho-hum for most people. It took a lot of work to drill that hole. And that was a test hole. We only drilled down about 1 centimeter, and we did that to try to understand the hardness. It was our one opportunity to really check out the system. Is it drilling? We've never drilled on Mars before. Is the sample actually being picked up, or are the tail lengths just blowing away in the wind? And so that looked like it was working, and so we did the full depth hole, which is about 2.5 inches deep there in the foreground. And then those dots that you see, that array of 5 that go across, and then you can also see down the full depth hole, there's an array of dots. Those are actually 1 gigawatt laser blasts from our ChemCam laser that's on board the head of the rover. And so we pulse the laser and generate a plasma off the rock, and then use a telescope to analyze the spectra coming off that. And so we had the sample that we were getting ready to analyze with our organic chemistry and X-ray diffractometers, but at the same time, we were able to look at the spectra and see initially, wow, this is something different. This isn't just Mars dirt. And then we also blasted, as you can see, down the wall of that hole so we could look for any variations through the depth. We then moved that material. Again, Curiosity is a geologist. So as a geologist, you have sieves. And so we move the material through, and it's done through a series of motions of the robotic arm so that the soil moves through the system so that we can separate into 150 micron particle size. We have a 1 millimeter sieve. And eventually, we get it ready to be portioned into our analytical laboratories. The first thing we did is we moved it into the scoop and opened it up and looked at it because we wanted to make sure we actually had sample before we tried to send it to the instruments. And what you can see immediately is that red dust along the back of the scoop there was dust from rock nests. That was some of the sand dune material. And the color here is very different. And geologists out in the field, like one of the speakers mentioned earlier, they look for shiny objects, right? Well, look at that. In fact, that's one of our toughest challenges is trying to keep the scientists allowing us to move ahead with what we want to do because they saw something neat over there, or somebody on the internet found something that we should go look at. And so this green-gray color of material we found very interesting. So we looked at it with our X-ray diffractometer. We looked at it with our tunable laser spectrometer, our quadrupole mass spec, gas chromatograph, all those. And we found water, which was to be expected. We found phyllosilicates, clays. We found chlorohydrocarbons. We started finding some very, very interesting things. And you couple this with the data from the laser, some of the other measurements that we've taken. We have an alpha particle spectrometer at the end of the arm. And all of the data we got as we drove. And the science community was able to determine that Mars was a very wet place. Right? There's clear evidence of water erosion. And we know the water still persists today. This is an area of neutral pH, not too acidic, not too basic. It contains energy gradients, various oxidation states, so that iron oxide, that deep red material, versus this green-gray. And we know from extreme biology, extremophiles here on Earth, they don't need energy from the sun to survive. They can actually thrive off of energy gradients in the soil. This area was mildly salty. If we were there at a time when water was flowing up to our ankles, we could scoop up that water and drink it, and it would actually taste quite good and refreshing to us. We also found all of the key chemical elements for life as we know it. And so the unanimous conclusion among the science team was that the conditions in the past, and maybe still in the present, but certainly in the past when Mars was wet, were favorable for life. We declared habitability of Mars in the past, which is 7 months into the mission, we hit one of the prime science objectives. Going back to Martian cows, or cows in general, which were mentioned earlier, we recently proved that there are no Martian cows. We did that by not detecting any methane down to 1.3 parts per billion in the atmosphere. And my younger daughter would say, well, that's just because there's no Martian grass. Duh, right? So we found other things like isotopic ratios of the atmosphere are such that that it's an indication that Mars has lost a significant amount of its atmosphere over time. We also learned some subtleties about the makeup of the atmosphere of Mars. So where's Curiosity today? The picture in the upper left is the 100-mile diameter Gale crater with this Australia-shaped mountain, Mount Sharp, there in the center of it. And you can see from where we landed there, which we named Bradbury Landing after Ray Bradbury, we drove about 400 meters off to the east to the area where we found habitability. And then we've been slowly making a beeline to the southwest, heading towards Mount Sharp. We've gone about 3.5 kilometers in a little over an Earth year. So you compare that to going 350 million miles in 253 days or something. We've gone nowhere near that once you're down on the surface, partially because there's so many shiny objects around to look at. So this is what awaits. This is the direction we're traveling in. This is Mount Sharp, invisible light. You'll sometimes see when we put the images out, we've got the raw images, which are very red in color because of the atmosphere. And then what we do is we color balance them in post-processing so that to try to get the atmosphere to be what the atmosphere would be on Earth, so that we could see what it would look like if it were on Earth. That way the scientists could say, okay, I see the relationships of the colors, let's go that way because that might tell us something. And so this is a white balanced picture. That dark material in the foreground are sand dunes that we're going to have to cross to get to Mount Sharp, and then we'll be working our way up. That boulder there is the size of the rover. The rover is 7 feet tall and about 9 feet long and 9 feet wide. So it will be pretty interesting and pretty spectacular as we get there. We're about a third of the way there now. So we're talking 6 to 12 months, depending upon the number of shiny objects, before we hit the lower slopes and start working our way up. So what's the future of Mars exploration? We've got this rover that we hope will go for a long time. It was designed for 1 Mars year, which is 2 Earth years, but we hope it will go a lot longer than that. And we certainly test it to 3 times that without any kind of failure. Well, I won't bore you with this chart, but what you can see from this chart going back to Mars Pathfinder there in the upper left is that we've been on a theme of follow the water. We knew water was on Mars, and so we wanted to follow it to understand the role of water in the evolution of Mars. Also, of course, all of these are helping prepare for eventual human exploration of the planet. And so we started exploring habitability with Phoenix, finding the water ice, and now with Mars Science Laboratory, which, of course, we found Gale Crater to be a past habitable environment. And the next thread is really seeking signs of life. And how do you go about doing that? Well, there are preconditions that have to be met. Here you can see past habitable environment, which we've checked, we've got that. What's the potential for biosignature preservation? What's the likelihood in the harsh radiation environment on Mars that biosignatures could actually be preserved? And we're working on that. And that's all part of a rover that, comes from a science definition team that NASA's put together for a rover that we're planning on launching in 2020, which is how I'll end our talk today. Then looking for possible evidence, potential biosignatures. Can we find them? And again, that uses a combination of the next rover as well as labs on Earth. And of course, that requires us to bring samples back from Mars, which we want to do on future missions. And then ultimately getting a positive detection of past life, a definitive biosignature from Mars. So NASA, we envision a Curiosity-like rover. You see this blueprint here looks very much like Curiosity, drawing from the technologies, the entry, descent, and landing technologies, because we're talking about the same size vehicle, the same mobility system with the wheels and the suspension and everything, a similar suite of cameras. And so putting all this together to do rigorous science in situ there on the planet, looking at enabling the future by creating a cache of returnable samples. So collecting cores from wherever we end up going and putting them in a cache that we could ultimately on a future mission take back with us. And again, drawing on the heritage that we've now created with Mars Science Laboratory, Curiosity. This is a prototype cache. So this is a 31 sample cache. And you can see over there on the left, that would be a core, about 1 centimeter in diameter, about 3.5 inches long. I'm mixing units here. We like to do that to keep each other honest. We would be collecting these samples, placing them in a unit like this, so that ultimately on a future mission, another vehicle could cozy up to this rover with a Mars Ascent vehicle strapped to its back, put this canister inside the Mars Ascent vehicle, send it into orbit around Mars, and now either have it thrust itself back to Earth or send a third vehicle to rendezvous with it and take it back to Earth so that we could analyze it using the extensive labs that we have here on Earth. So I'll just end with the name of the rover. So right now we call it Mars 2020. M2020 is the term around the lab for people. And so ultimately there'll be a naming contest, and we can all sit here and envision what that name might be. What is it? What words embody the willingness to pursue projects like this, right? Going to explore other planets, or taking your talents and your technologies and trying to better our world, better our understanding of the world, which is what we try to do with these missions, better help your community. And so, words that come to mind: persistence, innovation, daring. So I just challenge you all to think about what is it that drives you and drives you to dare mighty things and try to do wonderful things with what you do. Thank you.
Hey, Jordan, do you want to stick around and do QA real quick for maybe like 2 or 3 questions? All right, so before we go into the next speaker, we got some feedback on Twitter, so thank you for sending this, that we were wanting to do more QA. So we're going to open it up for about 3 questions to anyone in the audience who has a question for Jordan.
Right in the center. So the question is a very detailed question on gas spectroscopy and how we go about analyzing that. And so I am not a mass spectroscopist. I'm a rocket scientist engineer that builds these things. But what I can tell you is that we certainly use very pure helium on board that we maintain a signature of. And so we we know what gases are present. We track all materials that we capture on, that we use to fly on board. So we have an extensive collection of what we actually took with us to Mars. And then the folks that do this for a living and have been doing this type of thing, I apologize for not having a very specific answer to your very specific question. They are able to, again, through this culture of criticism and deciding, is that really an observation or did we just smell Cape Canaveral? Which I can tell you the initial data we got, we smelled a lot of Cape Canaveral. And so eventually that methane went away and we knew all we had left was Mars. Next question. Yeah, so the question is, what do I see as the role of private industry, and are we looking to partner with private industry, and how does that work? So yes, private industry, so SpaceX, Elon Musk's company, I think is a great thing, other than they hire a lot of our young engineers, because it's not too far away from our lab. Most of them are coming back, though, over time. What they're doing is helping with an industry that has been around a long time, rockets. And he's trying to do it in innovative ways that help drive down the cost, increase the capability, the Moore's Law kind of thing, as applied to rockets, which we don't normally do, which I think is fantastic. We've had a very monopolized launch services organization over time, and so launch prices are pretty high. It's a significant percentage of any mission cost, and we would like to be able to get that down, and folks like SpaceX are helping us do that. So when it comes to whether private industry could embark on something like Mars Science Lab or sending rovers or people to Mars, that's much more of a challenge and much less likely. You can see from the history of trying to land on Mars, we don't have it, we're not into the design of a bicycle with landing on Mars yet. We're a long way from it. And so the amount of resources it takes, the amount of experience and data from really all over our nation and to some extent all over the world is required, which goes beyond the resources that a company has and tends to go beyond the motives that a company has in trying to move out on a project like that. Mars Science Lab was $2.5 billion to do, the Curiosity rover. And everybody says, why would you spend that kind of money on Mars? The answer is we didn't. We spent it here on Earth, right? Improving technologies and going a long way, and at the same time, having this other planet help us learn a little bit more about our own planet. Next question?
We probably have time for one more.
One more? Okay. Anyone? Oh, I'm sorry. Very good. Okay, so the question is, has what we learned from Curiosity helped accelerate or slow down future rovers or people going to Mars? From the standpoint of rovers, it helped tremendously. The landing was so successful, and that technique of using the sky crane was proven out to the point that almost immediately NASA headquarters could envision how to use this architecture to further answer science questions. And so very quickly after we landed, they already had announced Mars 2020 and put together a science definition team to move out on what can we do with this, again, to help pave the path for human exploration, as well as continue to seek signs of life on the science themes. From the standpoint of the human exploration, that's a tougher question. We do have a radiation detector on board, and so we captured a lot of data that said that the environment between Earth and Mars is extremely harsh, and the environment on the surface of Mars is extremely harsh from a radiation standpoint. And so that puts some realism in what will be required in order to protect humans that want to go to Mars. We also saw the limitations of sky crane. It can take 1 ton to the surface of the planet, but it can't take the 50 tons or 100 tons necessary to get humans to the surface and then ultimately back off the surface. And so we don't yet have the follow-on technologies. We're starting to explore those. We think we know what those technologies are, but we're still a ways off.